Hi, I am Erwan Mazarico. I am a research scientist here at the NASA Goddard Space Flight Center, and I am a co-investigator on the VERITAS team. VERITAS will orbit for about 3 years around Venus in the primary mission, and we hope that maybe there could be an extension possible. But yes, the primary mission is about 3 years around Venus. The key component on the spacecraft for us is the transponder, the radio transponder, that will relay the signals from the Earth, transmit them back to the Earth, so that we can make a very good, precise frequency measurement. My background is actually I am from France. I was born in France and raised there, and so my primary education was in France, and including university. And at that time, I already had an interest in space science, and so I was looking for opportunities to have a career in space engineering or in science. And of course, NASA looms really big in everything that has been accomplished for that. During my PhD studies, I worked on analyzing the radio tracking data from Mars orbiting spacecraft. And so at that time, I was looking more into the density of the atmosphere very high up above the Martian surface. But those techniques that I learned, are directly applicable to learning about the gravity fields of planets. And so that's what gave me opportunities after my PhD to come work at NASA Center, the Goddard Space Flight Center, on a mission to the moon, the Lunar Reconnaissance Orbiter, and to map the gravity field of the moon, to learn about the topography of the moon with an instrument team here. And so from that point, I got really focused on geophysics of solid surfaces, solid planets. The VERITAS mission is the next NASA mission to study the solid planets, Venus, but the solid surface of Venus, and in particular the interior of Venus. And so it will map the surface at high resolution in terms of the morphology of the features, such as the volcanoes. It will also look into the rock type of the surface through the emissivity mapper. And my role in it is also through the gravity mapping to be able to say, how thick the Venusian crust is, where the density anomalies that may be indicative of current processes are located. Yeah, so for gravity mapping, what we do is that actually we used not an instrument on the spacecraft, but we used the spacecraft itself as a probe complexity of Venus, meaning that there's topography on the planet, there's maybe variations in crustal thickness, maybe density anomalies in the mantle. All of those contribute to a not uniform path of the spacecraft around the planet that we would expect from just, a very simple spherical Venus. And so by looking at the slight variations and changes in the trajectory, we can backtrack that to build a gravity field model. And so what we do is look at the radio signals that are exchanged between the spacecraft and the ground station on Earth. And with, very exquisite measurements of the frequency of those signals, we can constrain the path of the spacecraft around Venus. Yes, so the goal of mapping gravity fields is really to be able to probe the interior structure of the planet. So when we get a detailed gravity field map of Venus, what we'll be able to say, when we compare that to the topography that's measured as well, is we'll be able to say where the crust is maybe denser or less dense, and that could indicate more volcanic activity or a thicker crust. And putting that together with other evidence and geological mapping, we'll be able to learn about the history and the evolution and the formation of certain features, some of them of which are unique to Venus. So that will help us understand the tectonic processes that govern the upper crust of planets in general. Yeah, so currently for VERITAS, because we have not launched yet, and we are, still refining the design of the spacecraft and the mission, is really related to making sure that the current plan, the current capabilities that we think we'll get, will meet our science goals and requirements. And so currently we're working on simulations, and so making sure we understand the robustness of our investigation and the margins that we have on meeting our requirements. And also on refining the analysis of the analysis techniques, I should say, of that. So we proposed our investigation with the state of the art a few years ago, but we want to keep improving that state of the art so that we can get the most science returns for the mission. And also now we have more of a chance of really working with the other instruments and the whole team to try to build at sort of more of a working group level, try to build analysis techniques that will use multiple instruments data rather than single investigation. So the biggest challenge for any investigation after selection, but before we launch, is that there's a lot of trades going on. There's some uncertainty into how the implementation will actually be done, and so we're looking at different scenarios, and so the challenge is to keep the eye on the ball and make sure we preserve our capability to do the requirements while understanding that we need the whole team, not just gravity science investigation, to get to launch. So when I say trade, I mean trade-off study, meaning that if, for example, some subsystem or maybe the mass of the spacecraft could be significantly improved by giving up a little thing on one other side of for someone else, is it a worthwhile trade? And so sometimes trade studies can be done within your own investigation, but sometimes it involves, if we give up a little bit here and we gain a lot there, is that a worthwhile thing to think about? Yeah, so one of the main types of simulations we do is actually to simulate the whole mission as far as the gravity science investigation is concerned. So we will simulate the spacecraft orbiting Venus for several years and simulate every day having a contact with a ground station on Earth and simulate exactly what the geometry is, the noise on each measurement, and then fold those thousands and thousands of measurements together to see what does it mean for our precision on the gravity field map that we'll obtain eventually. Yeah, so the simulations we do are really all done on the computer. Currently, because the VERITAS mission and the gravity investigation is going to be very capable, we hope to obtain a very accurate field at pretty high resolution. And so those computer simulations can be quite costly. They can take several weeks to run sometimes. And so, we're still trying to refine and improve the efficiency, but those are doable. It's just you need to be a little careful about how many and what to do when you start them up. Yeah, so one thing that I'm interested to follow in the next few years is the return of NASA to the moon. One of the big drives for me as well to be interested in space science was, the Apollo landings and seeing people on the moon. And so the fact that, this may be very close to us now, again, and for the first time in my lifetime, that's definitely something that is, exciting. And I'm not directly involved in, the astronaut program or anything like this, but this is something very important to me personally and obviously to the agency as a whole. So I always had something for Venus, growing up and looking at books about the solar system. And when I was in undergrad, there was a project we had to do, and I chose something to do with the Venus atmosphere. And at that time, I was not really pursuing anything space science related. But I think, that followed me throughout. And when I started grad school and after that as a postdoc, there was no opportunity to work on Venus. There was no mission, there was no new data. And so when Venus missions that were a great geophysical interest, started to be proposed, I was really eager to participate and be involved. And so, luckily, I got involved with VERITAS, and I'm now on the team, and looking forward to learning about Venus.